That was off. Okay, now it's on. Sorry. Everybody woke up.
Great. It's Châu 5. Time to start. Welcome everybody to the first Asiacrypt session on side channel analysis and leakage resilience. And the first talk of this session will be given by Amin Morati, with the co-author for his paper being Tobias Schneider. The title of this work is Side Channel Analysis Protection and Low Latency in Action, Case Study of Prince and Midori.
Okay, thank you. Yeah, let's see why I'm here actually, to a bit motivate what the topic is and what is the motivation to give such a talk, is that I need to remind you about the low latency and low latency encryption and decryption and why it's needed. And it actually it's actually initiated a couple of years ago by industry sector that say that we want to have low latency ciphers or low latency encryption and decryption at the same time to support memory encryption. Just suppose that you have a system on chip, you have a complete system, embedded system, it has a microcontroller or microprocessor and wants to save or read from the memory, but the data that should be written in the memory should be encrypted. And then if you just stay with the, let's say, standard ciphers or the known ciphers, like for instance AES, and then you have a pretty, let's say, normal implementation of the AES, which is a round-based architecture, it needs minimum 10 clock cycles. And then every time that you want to read from the memory or you want to write into the memory, you need to wait 10 clock cycles. Then of course it's not optimum. Then you prefer to have a lower latency, means that the software is able to react, or the implementation react very fast in a way that it's somehow synchronized with the clock cycle of the microcontroller, microprocessor, and then in every clock cycle that you can write or read from the memory, at the same time you can encrypt and decrypt the data that you write the encrypted data into the memory and read afterwards the decrypted data from the memory. But actually, why memory encryption is required? Of course, in the scenarios that the chip is in the hand of the attacker, because the attacker may be able to open the chip, let's say read the memory content or dump the memory content, and then for that reason to be against such an attacker or to protect against such an attacker, you go for memory encryption. Otherwise, there is no, in my point of view, no reason to have the memory encryption, right? And then if we have such a scenario that we think that the device is in the hand of the attackers, that should we not care about the side channel leakage of the implementation? Or say just, yeah, we don't care, just the device doesn't matter, it leaks information, but the memory is encrypted. To this sense, we have tried to see what are the options when you want to have the low latency implementation of the ciphers. Let's say the best known or the first proposal was Prince. What happens if you want to have also side channel protection at the same time and such an implementation? For instance, we look at the Prince. Here is the design of the Prince. It has 5 forward rounds and 5 backward rounds. And I don't go to much details, but it has, of course, a SPOCs. You have the mixed column, shift rows, and key addition, and also round constant, which are added to the state. And lowest latency can be achieved by fully unrolled architecture. It means that if you have implemented this cipher this design in fully combinatorial circuit means that only gates, there is no register at all. Once you put the input here, either plaintext or ciphertext, and then set, of course, the parameter like the key and also whether you want encryption or decryption, then after a particular time, the ciphertext is ready. And this time, of course, depends on how large the system is, how many gates you have, and actually, which is defined by the latency of whole of this combinatorial circuit. This is a graph here. You can have an idea about how fast or how slow this implementation is. If you want a very fast implementation, which is the minimum for prints in the technology that we consider is 9 nanoseconds, and then you end up with roughly or more than 17,000 gate equivalents. Or if you want to have a smaller implementation, let's say around 9,000 gate equivalents, you reach in the areas or around 13 nanoseconds. Of course, this is for one particular library and technology. If you change the technology, this figure changes. Then the idea was single cycle fashion or single cycle implementation, fully unrolled architecture that is completely between the processor and the memory. Then you don't need to care about anything, just you give the plaintext, the ciphertext is ready after, let's say, maximum 30 nanoseconds or 9 nanoseconds, or other way around for the decryption. Good. Now, if you want to have the side channel protection, we have a couple of different schemes. Of course, we have heuristic and ad hoc schemes, like noise addition, shuffling, temporal randomization, and so on. For instance, you can for sure add noise addition to such an implementation, to a fully unrolled architecture. It doesn't matter. Of course, it increases the noise, and then the attacker, of course, has a bit more difficulties to perform the attack, depending on the level of the noise that you add. Shuffling most likely is not possible here, because you don't have any register, you don't have any order of the computations. This is just fully combinatorial circuit, and then you don't have any chance to change the temporal order of the operations, the same for the temporal randomization. But then on the other side, we can go for theoretically sound schemes like masking, that we call it in side channel analysis, or side channel area masking, which is actually just a secret sharing and multi-party computation. This is the same concept, but since we are using very simple scenarios of secret sharing and multi-party computation, which is a Boolean secret sharing, we call it usually masking and Boolean masking. And we have threshold implementation, in short TI, which is a correct way of implementing Boolean masking in hardware. Now, let's say shortly I will review the TI and the concept of TI, and then we come back to the prints and see what happens. Minimum number of shares means that the number of shares that you need to implement the secret sharing scheme depends on the algebraic degree of the sparks of the nonlinear functions that you have. For instance, in the case of prints, or let's say for most of the 4-bit, all of the ciphers that they are using 4-bit bijections, the sparks is a cubic function, which is algebraic degree of 3, and then for first order security, it directly mapped to minimum 4 shares you need to implement. Or you can decompose the function, this cubic function, to 2 quadratic functions. I mean, this is a quadratic function, another one quadratic function, and then instead of 4 shares, you can implement it with 3 shares. And then you need to put a register in between. If you don't put a register between these 2 stages, then of course, again, you have a big combinatorial circuit which works with 3 shares, and the algebraic degree of this, of the function that it realizes is again 3, and then with 3 shares, of course, you cannot implement this. Then definitely this leaks. Then you have to put the register between quadratic parts if you go for minimum number of shares. But putting the register between these decomposed functions or between the nonlinear functions, it's already contradicting with a single cycle fashion that you require for fully unrolled architectures that you say low latency implementations. A bit more about this, we come back to this concept a bit later, but just imagine that this implements the sparks, let's say X, and Z, X is the input of the SPOX, and Z is the output of the SPOX, and then I represent X with 3 shares in a way that if I XOR all these 3, I get the X, and if I XOR all these 3, I get Z, which will be the X input of the SPOX, Z output of the SPOX. Yeah, this is a Boolean sharing here, and another one Boolean sharing of the output. There are a couple of properties for the TI that you should fulfill if the implementation of TI is correct. We come back to this later. You can, I mean, I heard a couple of times mainly from industry that, yeah, let's have some heuristic ad hoc architecture, means that instead of fully protect the implementation, just protect the first round and the last round. I mean, the things that the attacker can predict if, of course, if the plaintext or ciphertext are not controlled. If they are controlled, you can extend the attack to the second round. But just imagine with this situation that the first round of the cipher and the second round of the cipher should be implemented, and then still you want to stay with the unrolled architecture. Means that you share the input in 4 shares. As I said, this is a cubic function, and minimum you need 4 shares. And then you have a cubic shared representation of the cubic functions with 4 shares. And then after first round is done, then you XOR again the shares, and then these rounds are processed in an unshared way. And then again, last round, again you make a new sharing of the middle value before the last round, and again, the last round is a shared implementation. This is not a correct realization of TI. Of course, this will leak. Yeah, I mean, we know this. I mean, this is clear. You don't have register here first of all, and after that, this part is already leaking the data, which depends on the, let's say, the output of the first round, and these are already predictable. But this is a fully unrolled architecture. It means that you don't control this part, how they are implemented. Of course, these parts which are gray should be controlled in a way that the shares are not mixed together. But this is not a correct implementation. But because I heard this a couple of times, that let's have some kind of a crazy ideas like this, which is not the correct way. What is the achievement of this? If you implement this and then measure the power traces, this is a PGA-based evaluations. Here, at the left side is the unprotected, unrolled implementation, and the right side is the TI protected, but of course it's still IL TI protected, unrolled. And then the power consumption is of course increased roughly 3 times because the circuit is of course much larger. And then the evaluations that we have done is based on first t-tests. I mean, if you are familiar with the t-test, you can have kind of a leakage assessment, whether the design or the implementation has leakage, depending on the intermediate values. With a complete random versus fixed t-test, we have performed here with 1 million traces, and the other side, and the unrolled version with 100 million traces. And then this is clear that it should leak. This is unprotected, and the other one still has leakage, yeah, which, as I said, is expected because the first round and only the last round are protected, and then the XOR that make the, again, unshared value leaks. You can also have the SNR, which calculate the signal-to-noise ratio based on the plaintext nibbles, because the SPOX is a 4-bit, and then instead of because the bijection is, the SPOX is a bijection and the key addition is also linear, you can have compute SNR based on the plaintext nibble, which will directly map to the way if you calculate the SNR based on, let's say, SPOX input or a SPOX output. In this case, the SNR decreases here. If you see, it's pretty small, but 10 to the minus 3, and here 10 to the minus 5. The SNR is pretty small, means that the leakage is reduced, but you cannot say that this implementation is provably secure. Of course, this is ELTI, but it reduces the leakage. And then the question is, what are the other solutions? If you want to have a provably secure design, then you have to stay with a round-based architecture. There is no way. You have to put the registers. And then this is the upper part figure is the original design of the round-based architecture. You have here the register, again, for the prints, for encryption and decryption. It has 2 paths, SPOX and a SPOX inverse, because it has forward round and a backward round. And if you want to make the TI or the Boolean mask version of this, you have to implement and S inverse, which are pretty large circuits, because nonlinear parts. And we have observed that the Spox and Spox inverse are actually affine equivalent in Prince, and then you can just have one instance of them, doesn't matter a Spox or a Spox inverse. We check a Spox inverse was a bit more optimized than a Spox, and then with two other affine functions, if you go from this way, you implement a Spox. If you go from this way, you implement the Spox inverse. Now, then you have one instance of the Spox instead of two that let's say, reduce the complexity or the size of the circuit if you implement it with TI. It means that this design is not necessarily smaller than this in an unprotected scenario, but in the protected scenario, if you want to implement the mask version of this box, the below one should be smaller than the upper one. First problem is how do you correctly implement the TI of a Spox with 3 shares? Unfortunately, it has to be decomposed in 3 stages, because one property of the TI is uniformity. It means that if you implement the Spox, again, I come back to that slide that we discussed here. Oops, it's pretty slow reacting to my buttons. Okay, this implementation. If you see this G function as which receive 3 inputs and 3 outputs, if you consider as a bijection again, as a function again, which let's say 3 times input, 3 times output, it should be also a bijection. Otherwise, the output that you have here, of course, it's a correct sharing of the output of this part, or also the correct sharing of the Spox output, but this is not a uniform sharing. And then when it's not uniform sharing, the next rounds, when this input is going to other nonlinear functions, it means that you share the input with a mask, or let's say with mask or random data, that they are biased. They are not uniformly distributed. Then you have to achieve the uniformity of the implementation as well in the TI scenario. Now, to achieve the uniformity of the present Spox, you have to decompose it in 3 stages, which is actually known. This is not our founding. And then there are different ways. These names actually are corresponding to some definitions that have been published before, which are the quadratic function and then some classification by researchers in Leuven. And then when you decompose it in this way, and then there are affine transformation between quadratic functions, and then you implement it with 3 stages. It means that you have to put one register here, one register after the first quadratic functions, one register after the second quadratic functions, and of course a third quadratic function, C, one register here as a state register. It means that you have to have 3 stages and 3 registers, which directly affects on the latency that you have. If you implement this, then you have to wait, let's say number of clock cycle is 10, and then 10 times 3, you have to wait till the output is available, right? If you have another Spox which could be decomposed in 2 stages, then of course it reduces the latency for you. But there are other Spox families in the Prince that they are offered, suggested, but all of them unfortunately need to be shared in 3 stages. It means that there is no difference if you change the Spox, one of those Spoxes which are suggested by Prince. If you now measure this, again, FPGA implementation, the power consumption is reduced, but of course you have more rounds. Instead of one big peak that we have seen here, there are clock cycles, and this design was running at a pretty low frequency, and 3 megahertz, I believe. And then with the t-test, it shows you that with 100 million traces, you don't have a first-order leakage, which was expected, which was our goal. Of course, because this is a first-order secure implementation, then second-order leakage and third-order leakage are detectable for sure. Yeah, but to avoid this leakage, then you can easily add noise addition. Then the noise addition plus the first-order secure implementation will make this practically hard to detect or to exploit. Now, the idea was that, yeah, we have seen this, but we don't want to have a round-based implementation because we have to make a fast clock in the design. And the industry was saying that, no, if you have a fast clock to achieve that low latency, then we need to add another source of the clock, which let's say works at 100 megahertz, but it takes energy, it consumes energy. And when the encryption function doesn't work, it just consumes energy, and this is not possible, and we don't want this. Or sometimes you need to go, for instance, let's say for clock frequency of 400 megahertz to achieve the lowest latency for that round-based architecture. But not on all platforms, let's say 400 megahertz is possible. Then the idea was to, let's use asynchronous logic. Probably you have not heard about asynchronous logic. I don't know. If you're electrical engineer, you have probably heard that asynchronous logic is pretty different to synchronous logic. Means that every gate has kind of acknowledgement and request. Means that when the gates are finish their evaluation, they send the data to the next gate, and the next gate evaluates. And some kind of a evaluation waveform, which is cascaded to the whole of the circuit, and then the circuit or the gates actually do not have any glitches, and then you don't need to, in theory, put register in your design. It means that all the gates are completely glitch-free, and then you can implement whole of a design in a loop way, and then when the design, the computation is done by the design will give you a signal that the computation is done. The idea was to use, let's use the asynchronous logic to avoid the fast clock in the circuit, and then see which achievements we have. If you are familiar with the side channel logic styles, it's very, very close, very similar to the concept of WDDL, which is a wave dynamic differential logic proposed in 2004 as a side channel countermeasure, or actually reducing the leakage of the side channel. Now, this is a asynchronous round-based TI, but we have to, again, put the registers. You see the registers here again? The problem is that if you remove the registers between the stages, again, this will be a fully combinatorial circuit, these two parts, that they are working, again, on 3 shares, but the algebraic degree of this is still, again, more than 2, and then you have definitely the leakage. Then you have to put the registers, but the point is you can have another part of the circuit which triggers this register. It means it's completely independent of the clock, but when the computation is here done, it says the register save. And again, the next part, when the computation is done, it says, okay, save, and so on. Then this circuit needs only one signal to say a start, and then when it's done based on the control signal, control logic, it tells you a done signal and I'm done, without any external clock. But if you implement this, again on FPGA, it was pretty hard to implement in FPGA because asynchronous circuits are not made to be implemented in an FPGA, or let's say FPGAs are not designed or fabricated to implement or realize the asynchronous logic. Then you see here the small clocks. Actually, the clocks are internally generated by the system itself. This is the active for the registers. But unfortunately, again, you see the first order leakage. Of course, this is a very small with 100 million traces, but if you want to stay again with the provable security, this is not what you wanted. If you want to see this and say, oh, the leakage is small, you could stay with the first design, as I said. Just first and last round are protected, and then your design would be similar to this. The reason for that actually is coming from the asynchronous concept. If you look more, let's say, carefully here, these registers are triggered by one function here. The function will tell when the computation of all these 3 are done and say, okay, save in this. Or even one of them done and second one is done, third one is done, then save in the register. The problem is that this is already, a linear, it's a non-linear function over these shares. Means that when all of them are done, then save. Then you are already leaking information about these 3 shares. Yeah, that is the source of the leakage. Yeah, and the good thing, I mean, if you come back to the TI concept, the TI initially proposed to be secure in presence of glitches. Yeah, and then. But actually, it also has a synchronous design which avoids this timing dependency. It means that unintentionally, the design of TI was synchronizing all these stages and then made that the second stage starts completely independent of the first stage. And then it avoids such a leakage that we see with asynchronous logic. Then the one conclusion here that TI and a synchronous circuit is actually the incorrect construction. I mean, you cannot easily combine TI and a synchronous circuit. Then just very shortly about Midori, what happens in Midori is, again, round-based architecture. And you know probably Midori has been designed, of course, Midori 64 is broken, but Midori has been designed to have the shortest latency in a round-based architecture, which actually fits very good to here. And then the sparks of Midori compared to Prince can be decomposed in two stages to have a correct TI. Then in theory, the latency of Midori, if implemented in this fashion, is better, which means that the latency is shorter. But now, the one question was that how do we deal with the fast clock? You can internally generate the fast clock. This is the engineering part, probably completely out of the scope of the crypto, but you can generate the clock internally of the system and then have just some control signals to say that this ring oscillator should start and when should stop working. And then without any external clock, which always working and consuming energy, you can implement and run the system. As a last slide, I run out of the time already. This is, for instance, the synchronous run-based TI with a fast internal clock. And then, again, you see here small clocks which are generated by the internal oscillator, and this large peak is because of a lot of clock cycle and a lot of rounds are running at the same time or after each other. And then the problem that we have seen with asynchronous circuit is gone. We have the first order security, and the second order, as I said, should be expected, or in this time, just a matter of chance that the third order leakage has not been seen. That was not the last slide, sorry. Here, a very short comparison, what happens. The circuit with the asynchronous design is extremely larger compared to the round-based TI, for instance. You compare these two. I mean, the upper one is for the shortest, for the smallest design, and this number is for the shortest latency. And then these are extremely larger, let's say around 3 times larger. And then the gain is actually very, very low. And then the circuit is very larger compared to this one because it has 2 phases of the evaluation and pre-charge. But if you look at the Midori again, the latency is shorter and the design is also lower, smaller because of the sparks. Yeah, of course, as I said, the Midori is broken, then probably it makes sense to design something similar to Midori, but not with the known leakage that, or let's say the weakness that the Midori has. Okay, thank you so much, and sorry for spending a lot of time.
Let's thank the speaker. Are there any questions or comments? Yes.
Okay, thanks, Amir, for a very interesting presentation. So if you have a fast internal clock, which was one of the solutions you were proposing near the end, does it not really defeat the purpose of low latency crypto to begin with? If you know what I mean? Because you do not necessarily need to go towards symmetric key crypto designs that can be very fast inside one clock cycle, because you're using more clock cycles anyway. Do you understand my question? Or I don't.
Probably did not understand your correction correctly.
So a design like Prince is specifically optimized to be implemented very efficiently, or I mean with a very low latency, assuming that you need to be able to execute the entire block cipher call inside one clock cycle.
Unrolled, fully unrolled.
Fully unrolled. And if this restriction is not really there anymore because we have a fast internal clock anyway, then maybe we're not really going towards designs like Prince, but other designs could be very suitable as well.
I wouldn't say that, for instance, if you go for a fast clock, Midori is also better than Prince in this case. Yeah? I mean, even if you completely remove all the registers and fully unrolled, again, Midori should be still good compared to Prince. It's not much far away from Prince, Midori, in this case. But I cannot say that the other design probably work much better. The problem is that in the fully unrolled design, many gates are combined to the library, that the cells that are available in the library. And then just by trial and check, you can check whether how big is this design or what is the latency of this design. Yeah? I would say it's not contradicting with the let's say, main goal of having low latency cipher if you go for a round-based architecture. Of course, what makes sense or what is important is to have very low number of rounds, which you can see it also in Prince. Yeah, I mean, the Prince has a pretty low number of rounds compared to other ciphers which have 4-bit SBOCs.
It doesn't matter if you have a higher clock frequency, right?
No, it matters. No, it matters. Like, sorry, wait a second. Here, the latency is the number of clock cycles, right, multiplied by the critical path delay. Means that this is 31 multiplied by 4. This will be the latency, not the frequency. Not the frequency itself. The latency is that latency of when you give the plaintext and when the ciphertext is ready, which will be the number of clock cycles that you need multiplied by the critical path delay. And look at here, this is 40 by 4, and this is 31 by 4. Because just you have less number of rounds, or let's say because of the stages of the SBOCs, then let's say in total, the latency is shorter.
Just one more short question. Your results are given for ASICs, gate equivalent, but your evaluation is done in FPGAs.
Yep, correct.
To what extent this analysis done for FPGAs carries to ASIC?
I just did the evaluation, the side channel evaluation on FPGAs, not any, let's say, how big or how small or how fast is the implementation on the FPGA. Just because making actually the chip for this design, which definitely would take me one more year. Yeah, this is clear. But the security analysis, I would say we can trust on that. Yeah, with the FPGA design, because we were misusing the FPGA elements. Let's say for the case of particular for the asynchronous circuit, we were using every loop as a single gate to realize everything correctly. Yeah, and then I would say what we made in side channel leakage should not be much different to the ASIC one.
And there are no ASIC tools that would allow you to do analysis, using tools rather than real circuit.
You mean doing the simulation?
Right.
Okay. No, we have not.
It would be too time-consuming or impossible.
You mean if you use a simulation instead of practicing FPGA? Yeah, the problem is here, if you do the simulation, this is the time, right? Because you need to do that. If you want to have a good simulation, you need to have the simulation in the transistor domain, and then taking every trace, depending on what you have, but which may take around, let's say, in the fastest way, a couple of seconds, and then having 1 million traces or 100 million traces would not be feasible.
Okay, let's thank the speaker again.
Thank you.
Let's move to the second talk, which is entitled Characterization and Estimation of the Key Rank Distribution in the Context of Side Channel Evaluations. The co-authors are Daniel Martin, Luke Mather, Elizabeth Oswald, and Martin Stem. The talk will be given by Luke.
Okay, that's cool. Starting from the beginning. Okay, so this is a joint work with my colleagues from Bristol, Dan, Elizabeth, and Martijn. And the general theme for this talk is how to do side channel evaluations better. So the claim I want to make is that we're not evaluating the resistance of a device to non-invasive types of side channel attack, such as DPA, as well as we could be. So hopefully I want to convince you why that is and what we can do about it. But first, just to kind of motivate this, why this is important. So resistance to these attacks is encoded in several evaluation processes already. If you're manufacturing to a certain level within FIPS 143 or Common Criteria 3.1, you have to give evidence that you're resistant to these kind of attacks. There are billions of devices out there that have to or should be following these security guidelines. And the reason why an accurate evaluation in particular is important in this case is that SCA is almost always probabilistic in nature. So sometimes the attacker gets lucky. And as evaluators, we need to be able to say with some confidence how lucky that attacker can be. So the underlying motivation for this work was, there's been a recent trend in literature which suggests that we need to change how we view the outcome of our attacks. So I'll circle back around to what I mean by that. But the rough plan for this talk would be to explain how we do attacks at the moment, how we evaluate at the moment, and then how we need to change our view to include something that we call the rank of an attack. And then consequently, how we should modify our evaluation strategies to include this notion of a rank. Okay, so a very, very like 10,000-foot view of a side channel attack is this. You have an adversary that needs to gather measurements that we call traces. It needs to be power consumption, EM radiation. And the attacker hopes that those measurements contain some information leakage on the secret key used by the device. Then the attacker has to essentially define their strategy. And that consists of two main things. The first thing is a model for the leakage for the device. And that model can be guessed, derived, estimated. But in general, the adversary hopes it matches well what is going on inside the device. And the second thing the adversary needs is what's called a distinguisher, which is essentially just an overloaded term for a statistical method or an algorithm that compares the model leakage with the real leakage inside the measurements. So when the attack is run, you have a key spit out, which is the attack's best guess for what the key is, which the adversary can check using a known plain text or ciphertext pair. And in this current model, if this key is incorrect, then that's failure. The attack's failed. You have to start again. So I quickly want to discuss what affects success for an adversary. So some things are kind of systematic. If the adversary doesn't model the leakage correctly or picks a distinguisher or a technique that doesn't quite capture the dependencies in the leakage, then the attack's not going to do as well as it could do. But there's also random sources of error. There's environmental noise, there's countermeasure noise, and maybe measurement quality also matters. So the way evaluations happen at the moment is what I'd call an attack-based approach. So if you're a manufacturer and you have a device, you'll give an instance of the device with the crypto deployed on it to some guys in a laboratory, which can be internal or external. And using their kind of best knowledge, their best expertise, they'll define a list of attacks, and they'll run those attacks on the device and see what happens. And if they all fail, if they all don't produce the key, then you're going to conclude the device is secure. If one succeeds, then you kind of judge its strength quantitatively, which in general, I mean, there's a few properties assessed, such as the amount of time the adversary took, how much money they had to spend. But the kind of the big one is how many traces, how many measurements the adversary needed to get, because these are time-consuming and expensive to acquire. Okay, so back in 2012, some guys at SAC noticed that the adversary doesn't need this attack to be perfect. And they essentially defined a strategy for the adversary in which the adversary does the exact same thing as before, same measurements, same attack configuration. But they essentially, and I don't want to go into the detail as such, but they essentially described a method for the adversary to make use of some auxiliary information contained in the attack result. And the adversary does some what we call enumeration work. The adversary is able to essentially assign a score that's associated with the likelihood of all the key candidates being the correct one. And once you've done this, you're able to check the key candidates in order of their score. So essentially, actually, I think a good way of viewing attacks in this model is essentially an enhanced brute force search. You assume the adversary is going to check keys, and you assume that the side channel information, what it gives you is an ability to check keys in a cleverer order than just randomly. So going a little bit more formally, we say the rank of an attack is the number of keys the adversary has to check before it hits the correct one. So I have a kind of really simple illustration on the slide here. Let's assume we're attacking a block cipher with a 128-bit key. The adversary does this enumeration step and generates the keys in order of likelihood, checks, keeps on going until they find the correct one. So in this example, the rank of the attack is 2 to the 57. And the adversary has to enumerate and verify that many keys. I want to point out this is absolutely not the same as doing 2 to the 57 executions of AES. There's a lot more work involved. To give a rough idea, what happens is an attack produces several lists or several subsets of information that give information on the likelihood of certain portions of a key. And the adversary has to kind of be smart in how it grabs those little bits of information, combines them to give a likelihood for a single candidate key. Okay. So if we circle around to evaluation, and we consider rank now, we have some interesting questions. And an example of one is this. So if you have an attack that requires 10,000 measurements and some rank left over afterwards, and an attack that requires 5 times more measurements but requires less brute force work afterwards, which is better? And I think the answer actually is it really does depend on, firstly, on how many or how long it takes to get measurements, how difficult it is, and also on how difficult the enumeration is. So at this point, there has been some work done by people who do evaluations on how to make use of rank, or how to incorporate rank into evaluations. Where we started with this work was to say, kind of do the obvious thing and say, well, the rank is a random variable defined over the randomness in a fixed number of measurements. So if you pick an attack strategy, pick a fixed number of measurements, and run the attack several times using different freshly gathered acquisitions, you'll have different ranks come out. And the interesting question is, well, how different will these ranks be? And then you might ask, well, can we analytically compute this distribution? Because that would be nice and straightforward. But the answer is, unfortunately, no. If you are happy to make a lot of assumptions, then you could do this, although no one has yet. But in practice, if I gave someone a device tomorrow and said, compute this distribution, let's see what it looks like, they wouldn't be able to do it. And a second interesting question is, in side-channel literature, we normally care about averages or expectations. So success is normally defined as an average. How many times will I succeed on average? And so a good question is, how is looking at the expectation of this rank a good idea? Okay, so if no analytical approach is available, this essentially collapses to a pure statistics problem. The only option you have left is to estimate the distribution via repeated sampling. So what this means in practice is you have to fix your strategy, fix number of measurements, gather a fresh set of measurements each time, run the attack, and estimate the rank. And so questions we wanted to kind of answer were, what does the distribution of the rank actually look like? And secondly, in side-channel analysis, I don't know if you've ever been to a chess conference, but you'll see hundreds of different ways of constructing attacks, ranging from very, very complicated machine learning techniques that only apply in kind of niche scenarios to very, very simple general attacks that require as little as subtracting the mean as 2 data sets. And so we wanted to ask, well, does the distribution to rank look the same for attacks that follow wildly different strategies. Okay, but before I go into the results, actually the first thing we want as people doing evaluations is a way to, well, essentially a way to not have to check every single key in turn. As evaluators, you don't want to be doing this every single time you want to work out the rank of an attack. But because we know the key, we can use that information to basically get a fast approximation for what the rank actually is. So starting from, I guess, Eurocrypt 2013, people have tried to define methods for doing this. The majority provided an interval estimate. And actually, at Asiacrypt last year, one of my colleagues, Dan, described an algorithm that provides a point estimate. And this is one we like, and we think it's fast and accurate. And as part of this work, we spent a bit of time trying to make it better. So to quickly describe what we did, we made essentially several observations that reduced the runtime of it. And this allowed us to achieve quite a few orders of magnitude more precision and no additional runtime. And actually, the interesting thing here is that the observations we made didn't actually reduce the algorithmic complexity asymptotically. So it kind of shows that constants are important. And what this means in practice is that you can get a very accurate point estimate in, at most, a few seconds on a reasonably powerful workstation CPU. Okay, so the first thing we found, well, the first thing we did was essentially run hundreds of thousands of millions of attacks on our university computing cluster, and we basically varied everything from noise levels, attack strategies, numbers of measurements, and so on. And the kind of interesting thing we found was that the distribution of this rank doesn't really change, or is independent of all these things. And essentially, if you take attack strategy A, which uses a small number of traces, attack strategy B, which is cleverer, sorry, which is less clever but uses more traces, those attacks will produce a very similar looking distribution if they kind of do equally as well. So good attacks that produce low ranks produce distributions that look the same, and bad attacks that produce high ranked that have high ranks also have distributions that look similar. We don't know why this is. This is where this analytical route might be useful. So in this work, we stuck to trying to improve the evaluation process, but that is definitely something to look into. So this is an example of what the kind of evaluation that you can do. So we took a data set produced by one of my colleagues at Bristol, which was published as CHES 2015, which is a DPA attack on a fairly difficult target, so a device implementing AES and hardware, and where the attack strategy was, for those that are interested, is just a straightforward correlation power analysis using EM measurements. So we had maybe, I think, in the order of a few million traces. We took small subsets of those traces randomly, ran the exact same attack that these guys did, and estimated the rank. And that's what you can see plotted on this graph. So if I wear the kind of hat of an evaluator under the kind of what I said was the current way of doing things, the interesting part is kind of down here or here, which is where the attacker starts kind of winning perfectly. On average, this is around 80,000 traces. But the adversary starts getting a luckily perfect attack at around about 50,000 traces. And in fact, this is what my colleague Jake reported in his paper. Now, if you take rank into account, and let's assume that, I don't know, we want 80 bits of security, in some sense, which is this horizontal line here. The adversary actually starts beating that, starts winning, on average here, and I kind of wish I'd drawn lines now, but that's about 20,000 traces. And actually, 10% of the time, it actually wins somewhere between 10,000 and 15,000 traces. So that's kind of, those are quite big gaps in the number of measurements at which maybe you define success. Another interesting thing to look at is the kind of distribution side on. So this is a histogram of repeated attacks where the average rank after the attack was 2 to the 16. So also that's good for the adversary. That costs nothing to enumerate. And you can see that the distribution looks kind of normal. You have a little bit of censorship going on the left-hand side, because obviously you can't do better than rank 0 or rank 1, depending on how you define it. But you can see there is still a fair bit of variance going on. On average, 2 to 16 is really easy. A lot of the time I win perfectly, but sometimes I have to do more than 2 to the 40 work afterwards. And if you make these attacks slightly worse, you can see the distribution start to spread a bit more. And I think this is the most interesting one, where on average, the attacker has to do 2 to 64 enumeration work, which is a lot. I think the most we've ever done in our lab is 2 to the 50, and that took 700 calls for 1 day. But some of the time, I don't know what the percentages are, but maybe 10% of the time, it's actually quite easy. We're doing maybe 2 to 45. And, I don't know, 25, 30% of the time, the adversary is totally screwed. It has to do more than 2 to the 80. So this suggests, well, it seems pretty obvious, that you perhaps shouldn't look at averages. And essentially, the best thing to do is to define a threshold and look at when your distribution tail crosses that threshold. And if I keep going, you can see how this normal distribution shape continues. Okay. So our proposal for how evaluation should be done now, if you care about rank, is essentially to collapse it to a statistics problem. It's the only kind of way to do things, which requires repeated sampling from the distribution for an attack. In terms of statistics, this large variance, which is, I guess actually I didn't mention this, kind of in the positions, the unfortunate positions in which you're most interested. So as I'm guessing as a manufacturer, you're probably going to be interested in when ranks are around 2 to 60, 2 to 70, maybe even 2 to the 80. And this is where the distribution has the most variance. So consequently, we suggest that non-parametric order statistics, such as percentiles, kind of let you make a lot more actionable conclusions, such as the one I've kind of said here. One thing I haven't discussed here but is in the paper, is how many repeat experiments you should do. And we kind of heuristically arrived at 30, ideally more. This isn't great, because it does require these evaluators to gather a lot more measurements. You might be able to do something slightly clever with reusing some of your measurements, but you also need to be careful. But unfortunately, this is currently the only option we have. So I'd just like to point out, we implemented this estimation algorithm and the improvements we described. And we also have an implementation of the enumeration step for an adversary, which is designed to run on a lot of cores. And that's available at that URL. It's written in C++. It's a header in your library, so you can integrate it fairly easily. It has tests, comments, examples, and it's free to use, so please do. And any questions about it, please talk to me. And so with that, I'll conclude, and thanks for listening.
Let's thank the speaker. Are there any questions or comments?
in many cases, you can attack both the first subkey and the last subkey by doing encryptions and decryptions inside channel attacks, and you get two different rankings. Now, assuming that they are related, the first and the last key, for example, there are permutations of bit positions. That's the only difference between the first and the last key. Could you devise a better algorithm for doing ranking if you have a ranking over the key bits in one order and the ranking over the key bits in another order? You see what I mean?
So essentially there's a structure that you can exploit given
Exactly.
the algorithm you're targeting.
For example, in DES, the first subkey and the last subkey are just permutations of each other.
Yeah, that would be interesting, but I've never tried, yeah.
Any other questions? So following on the question, so I wonder, to what extent your analysis would apply and recommendations would apply to other ciphers. The implementation, your analysis was done for AES, right? So how do you think it would apply to other types of ciphers, maybe lightweight ciphers?
So off the top of my head, I think everything we tried was AES. Given kind of existing non-rank-based research into other ciphers, I would not expect any difference. I would still expect this kind of shape just shrunk, depending on the key size, and that would literally be all I would expect to see.
Okay, let's thank the speaker again. And let's move to the third talk, which is entitled Tailor Expansion of Maximum Likelihood Attacks for Masked and Shuffled Implementations. The co-authors are Nicolas Brunel, Antoine Guillon, Annalie Hauser, Olivier Ure, François Xavier Rondard, and Yannick Teglier. And Nicolas will give a talk.
Do you hear me well? Yes. So thank you for this nice introduction. So in this talk, I will present you our result on Taylor expansion of maximum likelihood attacks. The maximum likelihood attacks are known to be the best attacks, but in some cases, they can be really inefficient. And in this presentation, I will show you a new attack with a better efficiency. So this work is a joint work with my advisor, Sylvain Guillet, from Telecom Paritech and Secure IC, from Annelie Heuser from IRISA and Telecom Paritech, but also with Olivier Rioul from École Polytechnique and Telecom Paritech, with François-Xavier Standert from UCL, and this work has been done while Yannick Teglia was at ST. I will begin this talk by an introduction on side-channel analysis. Side-channel analysis are classical threats against cryptographic algorithms, and as a consequence, countermeasures have been developed. These countermeasures are themselves the target of particular kinds of side-channel attacks. In this scenario, when the attacker wants to apply the best attacks, we'll face the issue of the high complexity. And in the second part of this presentation, I will show you a new attack which kept the good properties of the good effectiveness of the optimal attacks, but with a better efficiency. I will then illustrate this new attack in a practical scenario. So side-channel analysis are a classical threats against cryptographic algorithms in embedded systems. They aim at revealing the secret data, such as the secret key, by exploiting the physical leakages emitted by the device during the execution of the algorithm. These leakages can be, for example, the electromagnetic emanation, or the power consumption, or even the heat. And as a consequence, some countermeasures have been developed. One of the most classical countermeasures are the masking scheme, as their security can be formally grounded. The rationale of an omega minus 1 order masking scheme is as follows. Any sensitive variable will be randomly split over omega shares using omega minus 1 random value called the masks. The impact of these two countermeasures is to make the first omega minus 1 order moments independent from the key. And as a consequence, if an attacker wants to attack such scheme, he should at least look at the omega moment. Another classical countermeasure is the shuffling. The idea of shuffling is to randomize the order of execution of independent operation in the algorithm. And this countermeasure needs a random permutation denoted in this talk by pi. So if the idea of, if in a normal implementation, we will start by use the value Z1 followed by Z2, Z3, and Z4. In a shuffle implementation, we will, for example, start by Z3, followed by Z1, then Z2, and finally Z4. The classical way to defeat such countermeasure is to make the sum over all the shuffled variables. And the consequences is that we add some noise, so the extrinsic noise, which are the the algorithmic noise, which are the non-targeted values, and also we also add all the extrinsic noises of the variables. These two countermeasures depend on some parameters. The most important parameters for masking scheme are omega, which is the number of shares. This number is strongly linked to the number of masks. If we want to have omega shares, we need omega minus 1 masks. The other important parameter is the order of the implementation. It's the minimal key-dependent statistical moment. At best, we have O is equal to omega. And if a masking scheme meets this property, it will be called a perfect masking scheme. In this talk, we assume that all the masking schemes are perfect. The most important parameter in the shuffling implementation is the size of the permutation, denoted by capital pi. These two countermeasures can be defeated by the template attacks. Template attacks are a particular kind of side-channel attacks. They are known to be the most powerful in an information theoretic sense. Such attacks can be divided into two phases. In an offline profiling, the leakage model is learned and by using a golden device in which we can modify the value of the keys. It exists different methods to perform this estimation. There is the non-parametric method, such as the histogram or the kernel method, or the parametric method, for example, the mixture models. The second step of the attack is to recover the key using the model learned during the offline profiling and by applying the maximum likelihood attacks. So I will present to you in this slide the main advantages and disadvantages of parametric method and non-parametric method. In parametric method, the only random part is the noise. It means that, in general, these methods are easy to estimate, as we can only compute means or variance. But because we assume that the only part is the noise, we assume that the shuffle and the mask are known. This means that we assume here a powerful attacker. And the other drawback is that it can lead to many templates. In non-parametric methods, the shuffle and the mask are part of the noise. And as a consequence, it's not need to know them. But this method can be difficult to estimate, as they may suffer of the curse of dimensionality, which is a common issue in machine learning and statistics. So in this presentation, we assume that all the models are perfectly known and estimated using parametric methods. In these presentations, the attacks are applied on Q queries, which are the leakage measurements, so the traces, and on D leakage sample. This value D is called the dimension of the attacks. Each leakage measurement can be modeled by a deterministic part and a random noisy part. The deterministic part, Y, is a function of a secret key, K star, a random plain text, T, which are n-bit words. But it also depends on some random values, which are the value used by the countermeasure, such as the mask and the shuffle. And in this presentation, these values are denoted by a capital R. The random noisy part is assumed to be a white random Gaussian noise with sigma square as variance. When the models are perfectly known, so we have shown in our 2014 Asiacrypt paper that when the model is known, the optimal distinguisher, meaning the distinguisher that maximizes the success rate, is the maximum likelihood. It consists in maximizing the sum over all the traces of the log likelihood. And we can see that in this formula, this expectation here is applied on R. So it's applied on all the masks and all the permutation. And in this presentation, for convenience, we have denoted by gamma the SNR, which has 1 over 2 power of 2 sigma square. Now, if we look at the complexity, we can see that its complexity depends on the number of traces, Q, on the dimension of the attack, D, but also on the number of possible share value. This value comes from the expectation over the masks, but it also depends on the possible permutation, which comes from the expectation over the permutation. And if the size of the permutation, pi, is high, this term, pi factorial, became huge. And as a consequence, the optimal distinguisher will not be computable due to its high complexity. So in this part, I will present you which is our main result. It's a rounded version of the optimal attacks, which kept the good properties of effectiveness of the optimal attacks, but with a smaller complexity. As already mentioned, the optimal attack consists in maximizing the sum over all traces of the log likelihood. But using the cumulant degenerating function, we can rewritten this formula as the sum over all traces of this series expansion. This series expansion depends on the value kappa, which are the high-order cumulants. The high-order cumulant can be expressed recursively using lower-order cumulant and the high-order moments. Now we can introduce our new attack, which is a rounded optimal attack. This attack depends on a parameter L, which is an arbitrary choice of the attacker. So our new attack is the rounded optimal L-degree attack, consists in maximizing the L-order Taylor expansion in the center of the log likelihood. In other words, we take the L-first terms of the previous expansion, series expansion. So we can see that the term used by the maximum likelihood is equal to the sum of the term used by our new attack and an error term where the small o is the Landau notation. This means that this error term is small compared to gamma to the L when the SNR is small. If we now look at the complexity of this new attack, we can see that this attack, the complexity still depends on the number of possible share values, so the expectation over the mask, the number of traces. But it also depends on 2 factorial terms. These terms depend on the dimension of the attack, on the degree of the Taylor expansion, so L, and the size of the permutation. And we can notice that when the degree of the Taylor expansion is small compared to the dimension of the attack, these 2 factorial terms are small. And as a consequence, this complexity is also small. So I will now illustrate this new attack in a practical scenario. As case study, we have chosen the case of a masking scheme with a shuffle table recomputation step. So it exists different implementation of masking scheme. They mainly differ by the way the non-linear parts are implemented. Indeed, the implementation on linear parts are quite obvious, but the implementation on non-linear one are more difficult. So we can cite the algebraic method, which exploits the algebraic representation of the non-linear part. We can also cite the global lookup table method, which all the value for all the possible masks are stored in a global lookup table. But we can also cite the table recomputation method, which pre-compute a mask Xbox stored in a table. This method are often used in practice as they represent a good trade-off between memory complexity and time complexity. Moreover, recently, this kind of implementation has been extended to high-order masking scheme. So the sketch of table recomputation algorithm is as follows. In the first part, the table is recomputed, and then it's the classical mask cipher. In the recomputation, we go from all the possible entry of the table and mask the input and mask the output. This kind of algorithm can be defeated by classical second-order attack. But it's known that better attacks will take into account the leakages of the table recomputation. A first example was given by Phan et al. In 2009, which recovered the mask by a first horizontal attack and then recovered the secret key by a first vertical attack. But a better attack is to apply the maximum likelihood and take into account all the leakages of the table recomputation and the cipher in once. In order to protect such implementation against this attack, the classical contour measure is to randomize the order of execution in the table recomputation, and it will need a random permutation here, 5. And here we are in the case of a shuffling. So, of course, this kind of algorithm can be still defeated by exploiting the leakages of the classical cipher, so by building bivariate attacks. So, for example, we can apply the second-order CPA, or the optimal distinguisher, as in this case, no shuffling is involved. But we can also apply our new rounded optimal attack, for example, at degree 2 or 4. So we can see in this figure the success rate expressed on the number of traces. So first of all, we can notice that the optimal attack here is the better attacks. We can also notice that our new attack at degree 2 and the second-order CPA perform similarly and are close to the optimal attacks. But the interesting fact in this figure is that our new attack at degree 4 is not as good as the other attacks. This means that in this case, we have added some term in the Taylor expansion which not make the attack better. And this is due to the fact that in this case, the noise, so for standard deviation is equal to 1, is not high enough to have a good approximation of the maximum likelihood by the Taylor expansion. Now, if the noise increases, for example, if sigma is equal to 2, we have still the success rate explained in the number of traces. We can see that all the attacks perform similarly and are close to the optimal distinguisher. Of course, better attacks will take into account the leakages of the table recomputation. In this case, the optimal distinguisher is not computable due to the term in 2 power n factorial. A first example of attacks which target shuffle table recomputation have been presented in CHES 2015. It's the multivariate attack on table recomputation, and it's a third-order attack. And we can also, in this case, apply our new rounded optimal distinguisher. We select as degree 3, as we know there is third-order leakages because of this attack. We can now study the complexity of this case study. So we can see that, of course, the optimal distinguisher is not computable due to these high factorial terms. And we can also notice that our new attack is longer to compute than the multivariate attack. But we will see later that it will give better results. Now we can see this figure that for noise sigma is equal to 3. We can see that the new attack, R up to 3, and the multivariate attacks perform similarly and are better than the second-order CPA. This means that in this case, the most important term in the Taylor expansion is the third degree 1. Now, when the noise increases, for example, for sigma is equal to 12, we can see that Now, the second order CPA is closer to our new attack. And we can also see that it's much better than the multivariate table recompilation attack. This means that in this case, the important term in the Taylor expansion is the second degree one. But we can also notice that because the new attack is better than the second order CPA, the third degree terms have still an impact. Now, for intermediate noises, we can see that for sigma is equal to 8, for example, our new attack is much better than the attack of the state of the art, as it needs 2 times less traces to reach the same level of success rate. For example, for 80% of success, we need around 60,000 traces to reach 80% of success for the new attack, while the other attack needs around 120,000 traces. For other value of noise, we can see that the gain is smaller, but still, our new attack is much better than the attack of the state of the art. We can see in the figure the number of traces needed to reach 80% of success, depending on the noise variance, on the noise standard deviation. And we can see that in all the noise scenario, our new attack is better than the attack of the state of the art, as this curve is below the curve of the multivariate attack and the second order CPA. So as a conclusion, we have shown in this presentation a new attack, which is a truncated version of the theoretical optimal distinguisher, which become efficient. This means that now the attacker can manage this attack, it can compute, and remains effective. Indeed, this attack is, in the case of the shuffle table recomputation, always better than the attack of the state of the art. Now the question arises is how to quantify the accuracy of the approximation. So in other words, how to choose the degree of the Taylor expansion. Indeed, we have seen that the good choice of the degree of the Taylor expansion will depend on several parameters, such as the noise variance, the dimension of the attack, and also, of course, the parameters of the countermeasure. So we can imagine that it will be a trade-off between the effectiveness and the efficiency to choose the good parameter, and it will be an interesting task will be to do this for a generic countermeasure implementation. So I hope we will have some questions, and thank you for your attention.
Thank the speaker. Any questions or comments? Yes?
You build the model, the deterministic part, and then there's a noise. What happens, what variation is there between one chip and another chip in the deterministic part that makes the the distinguisher then accuracy go down or not work anymore?
Sure. So we have done all our tests, assuming that, of course, the models are perfectly known. This means that we have no process variation between the two devices. And if it's the case, of course, there will be an important impact on the effectiveness of the effectiveness of the attack. So it will degrade the result of the attack, of course.
Were there any results in practice with this kind of strategy?
So yes, we have some practical results. So we make it on software with NatMega with 2 different cards. And in this case, we have matched the result we see here, exactly the same. We have so much difference between the two set of traces. So it was okay, but it doesn't mean in general it will be the case.
Thank you.
Yep. Are there any other questions or comments? So I wonder if your attack gives advantage also for the case of applying just masking without shuffling. If you have the case.
So if we have no shuffling, in fact, we are close to these cases. And in this case, of course, if our new attack is close to the second order CPA, so the advantages are small. But we can also imagine other scenarios where the devices leaks in different orders. So we can exploit second order attacks, but also third order attacks. And so on. And we guess that in this case, this approach will lead to better results than, for example, the second order CPA alone.
And how many degrees do you think are practical to check?
So in fact, it will depend, because in this case, we can easily check the higher order degrees. But now, for the multivariate case, we have to establish the exact formula of the Taylor expansion, and it's quite difficult in practice. So it's for degree 3, it's okay. For 4, it became difficult. So of course, if we had time, we assume here the result will be smaller, better. But I think in this case, it will be the best case.
Thank you. Any other questions, comments? If not, let's thank the speaker again. Let's move to the fourth talk. The title is Unknown Input Effects in the Parallel Setting, Improving the Security of the Chess 2012 Leakage Resilient PRF. And the authors are Marcel Medved, François Xavier Stondart, then Zdzislaw Nikov and Martin Heldhofer, and Marcel will talk.
Okay, thanks for the introduction. So today I want to speak about how to improve on the Chess 2012 leakage resilient PRF, but not only how to improve the security, but also we lower the requirements. So with our implementation, it is possible to implement it with a plain parallel AES implementation, which was not possible before, while keeping the same performance. Okay, I will start recapping the countermeasure landscape and the cost of countermeasures, and then motivate why PRFs or leakage resilient PRFs are useful, and then, evolve on the different constructions, ending with our construction, and then give some results on the analysis we've done and conclude. So we've already heard before that if we implement a cryptographic implementation like a block cipher on a device, we have several sources of side-channel information like the timing, which we need to keep constant, but also instantaneous leakage, which might come from power or EM. And also, just before, we've heard one of the things we want to do as an implementer is to keep the signal-to-noise ratio for these side-channel traces low, or apply masking to make the power consumption, the power consumption depends on the data processed in the device, and this one depends on the key. And we want to make the statistical moments in the leakage distribution independent of the key, at least the lower ones, by masking. And another thing we can do is to just limit the number of measurements an adversary can make, or in other words, limit the key usage. And then we have other problems we have to take care of, but we are not so much concerned about this in this particular talk. So I will focus on side-channel leakage. And for this, we have already seen, there are well-studied countermeasures, for instance, masking, which is the costs are quadratic in the number of shares, in a general case for an arbitrary circuit, and the security is exponential in the number of shares. Then we have time randomization, where both are linear, and then we also need fault protection. I don't discuss this in this talk, but our construction also gives advantages there. Also linear, and the real device must be protected against all of them. So you can basically multiply the costs of all of them, and that might be too much for a low-cost device, or it might be high in general. And also combining those countermeasures is not even straightforward, because sometimes the goals are contradicting each other. So adding redundancy might give more information in the trace, but that's not what you want for side-channel protection. And so one thing to do, as I said, is using key updates to limit the number of measurements. And one thing you could do, for instance, to limit the number of measurements is to implement this leakage resilient PRG or stream cipher. You can see that you start from a key and then you just go to the right, and in every stage you update the key and you also produce an output like a key stream. And in every stage the key is only used twice. So if you have a bounded leakage for the block cipher implementation, then you also have a bounded leakage for these two calls. And then for some constructions you can have a proof that you can run this basically as long as it's still secure in the black box model. And you will be fine, you will have bounded leakage for the whole construction. The problem is you can run this only once, because for a stream cipher, yeah, you need to update the seed every time. So the question is, how can we update this seed in a bounded leakage way? And okay, the first thing, or at least in the proofs, you often need a leak-free gadget to initialize first. And one thing you could do is to have a highly protected implementation, like masking. And then, well, overall, you might get better performance than always using a masked implementation, but you still have no bounded leakage. You can improve on the performance by using rekeying. There you usually have a special dedicated function for this seed update, which is linear, so that also masking has only linear costs, so you can mask to higher orders, but still you have no bounded leakage. And so that's one of the motivations for actually instantiating a leakage resilient PRF, which would allow you to initialize here with bounded leakage. And in this work, we attempt such a construction. We have no proof for this because, yeah, if you have, for instance, an adaptive leakage function, you can not really show something for hardware. But if we fix some assumptions like Hamming weight, leakage, and so on, we can at least conduct experiments which suggest that we have, well, very positive results on the bounded leakage side. So our construction works in a parallel setting, and therefore I will first talk about DPA attacks against a parallel implementation of AES. That means we have a plaintext input, ciphertext output, and inside everything goes on at the same time. So for instance, the first S-box layer. All 16 S-boxes are evaluated on the same time. And in an attack, we would collect traces for many different plaintexts, and we would then know these values, the plaintext bytes, P1, we would make a key guess, and this would allow us to predict the output here. And applying a leakage model, we can therefore predict the leakage of the device under a certain guessed key. And then having the actual leakage from the device measured, we can make a comparison and decide which one is the correct key. Of course, in a parallel implementation, we don't only leak about this intermediate value, but also about the others. Fortunately, our plaintext bytes are independent, and therefore, well, we can marginalize the distribution of these S-boxes, and therefore our noise produced by these S-boxes becomes independent algorithmic noise, which we can easily model and take into account during the attack. So eventually, if we have more algorithmic noise, we will need more traces, but we can always recover the key given enough traces. And eventually, we will get for every S-box, because we attack every S-box after each other, a score vector. So we get 16 score vectors suggesting the 16 key bytes. So this is how a plot of attack simulations. In our simulations, we always use noise-free Hamming weight leakage and perfectly computed templates. And you can see that, yeah, parallelism increases the algorithmic noise, and therefore we need more traces. On the y-axis, you have the guessing entropy of a single key byte in log scale, and on the x-axis, you have the number of traces needed also in log scale. So the purple one refers to a fully parallel AES implementation. The blue one, there is no algorithmic noise at all. And apart from the fact that algorithmic noise increases the number of needed traces, security decreases exponentially with the number of traces you have. But what's positive about it is that if you would be able to fix the number of plaintexts to 2, so the number of traces an adversary can get, then we see we have bounded leakage, which is not sufficient in the case of no algorithmic noise, but if we have enough algorithmic noise, this is already something we can work with. So the question is, how can we fix this in a practical scenario? to make it useful. And the answer is quite old. We can use the GGM PIF construction, which essentially works. We have a public input X, which we write as a bit string, and we have a key and we fix two plaintexts. In this case, we have the all 0 and the all 1 plaintext. And we start with the key, and if the first bit of X is a 0, we encrypt the all 0 plaintext, and otherwise the all 1 plaintext. And then we get a new, output is now our new key for the next iteration, and so we process the whole input X like this. And the nice thing here is we only have two plaintexts that we use, so we get only 2 traces per key. Of course, in practice, you can measure as often as you want, but since we are in a noise-free scenario, having 1 trace is good enough. So it's the optimum already. Problem is we need 128 encryptions, which might be too much in practice. So the question is, can you improve this in terms of performance? And well, naive way would be, okay, we just make this tree wider and we use more plaintexts in every stage. But as we saw before, security decreases exponentially. This is not an option. So then can we do better in terms of security? And at CHES 2012, the proposal was to have carefully chosen plaintexts. Imagine you take 1 byte of your input X and you just replicate it 16 times. And those form your 256 plaintexts. So all plaintext byte inputs to the S boxes are equal. And then if you mount your side channel attack, you get 2 interesting effects. First of all, the plaintexts are not independent anymore, and therefore this noise here becomes key dependent. And second, you can't help but attack all S boxes at the same time. So your attack doesn't give you 16 score vectors, but only 1. And then the 16 subkeys are hidden or are somewhere there. So we get the speed up. Divide and conquer doesn't work anymore. We have key-dependent noise. And even if we recover, so even after the attack, all 16 correct key bytes are ranked first, we still don't know their order. That's not too bad. Problem is for plain AES, 16 faculty is not big enough, so we need a different block cipher. Then also the property holds only for the first round, because later on the state bytes are not equal anymore. And also the 16 S boxes need the same leakage function, so we have this equal leakage assumption. Because if the leakage function for every S box is random, then it's the same as having random plaintexts. So can we do better than this? And this is now our contribution. What we propose is to use unknown plaintexts. And so we need a pre-computation step in which we first run the leakage resilient PRG and produce 256 secret plaintexts, for instance, plus 1 updated key, which we use as a root here for our new tree. And the way we run it is we just take 1 byte of X to index this table of secret plaintexts and then encrypt the secret plaintext. Of course, we need to take care that they are all distinct, but that's not a problem. It's also easy to show how to do this in a leakage-free way. What is interesting to see is, or not surprising, for 2 plaintexts we are already better than the GGM construction, because now we have 3 secret portions instead of 1. Okay, but the interesting thing is that it stays like this. We lose a bit, but not much. And so what happens here is that we now have all these bytes being secret, and in an attack, normal DPA doesn't work anymore because we don't know anything about the plaintext. So we need a template attack, but the templates need to, we need to evaluate information about the plaintext and about this intermediate value. So it's a second order plaintext template attack. And also, again, we can't target a single S box anymore in a parallel setting. We always target all of them at the same time. So we again get only a single score vector. So we need profile attacks. And this key-dependent noise, which we still have, now affects a 2-dimensional distribution. So it has much more impact and disturbs the attack much more. And also now this key-dependent noise property holds in the entire algorithm and not only in the first round. Okay. then we had these attack traces. We can look at what we can do to see what's happening. Is we can make models for all the distributions for the different subkeys, assuming, since we don't know the key, just uniform noise caused by uniform inputs. And at the same time, we compare this to the distribution we get from the device. And if we do this for carefully chosen plaintexts, we see that most of the time the correct key bytes have the closest distance to the device distribution, and that's why they are almost always ranked first. Compared to this, the unknown plaintexts, we have a much better scenario, and they look kind of much more scattered. So this is a single experiment. We did this several times to get the distribution of the ranks, and again, for the carefully chosen plaintexts, we see that they are. So this is the distribution of the subkeys in general, and you can see that they have very low ranks. And most of the time, the 16 bytes are ranked first, and then there are some outliers. Out of the 16, the best ranked one is always ranked first, and this can be used in an advanced attack. And then also to find the worst ranked out of the 16, you don't have to go very far, so usually rank 20 is sufficient. On the other hand, if you look at the distribution for the unknown plaintexts, it looks very much close to uniform, which would be a straight line. And so the median of the general rank distribution is 102 instead of 128 for a uniform distribution, and the median of the best ranked subkey distribution is 6 instead of 10, and then for the worst rank 240 instead of 245. And so we did this 40,000 times, and the best rank for the worst key was 110. So an intuitive complexity calculation would be 110. You need to go up to rank 110 to find all your subkey bytes. And then you can estimate the complexity like this. This is much more simplified, but okay. It's still above 2 to the 100 with probability smaller 1. So, okay. So I presented a leakage resilient PRF with bounded leakage under practical assumptions, with assumptions that are much fewer than for previous constructions. We have no equal leakage assumption. We don't need randomness for this countermeasure, actually. That's also nice. And it works with a plain parallel AES implementation. The speedup depends very much on the memory, and the trade-off is not very nice because for m times speedup we need 2 to the m memory, but for m equals 4 or 8 it's still okay. And then we did much more experiments in the paper, so we played with the leakage models to see if that has a bad impact or with implementation flaws and so on, and yeah, we got positive results for all of them. But of course it's a kind of new approach and it needs much more analysis. Like masking has been studied now for more than 10 years. Yeah, so more analysis is needed. And we also found out that the weakest point is the generation of the secret plaintext. So we need to take care of that. Yeah. Okay, I think I'm over time already. So thanks.
Let's thank the speaker.
Yeah.
Are there any questions or comments? Yes.
Can you get back to your contribution, the slide that you explained to your part?
You mean the drawing?
Yeah, exactly. The plaintext is that the plaintexts are unknown now, but they are selected once and they stay unchanged.
Yes, they depend on the key. So, I mean, here we attack the key, but since both are unknown, you can also turn around the game and you can go to the last iteration here, and you can fix the plaintext and you can just vary the key, and then so in this case, for the key, you only have 256 traces. If you mount an attack on a secret plaintext, you can have as many traces as you want. That's also why we extended this much. And we also did the rank distribution analysis was done using the full distribution. That's as if you would have all the traces at hand that exist. But the point is, if you do this, then you only got one plaintext. You have no way to verify it, so you need several of these to actually mount an attack on the keyback. And the complexity which you might have still, because you don't get the full plaintext, they kind of multiply with the number of plaintexts you need.
Compared to the previous one, when the plaintexts are selected intelligently,
Carefully,
as
yeah.
you said, yeah, you have more secrecy here, or?
Well, I mean, we always start from the same entropy. The point is that if we use the key with known plaintexts, we have only 2 fixed, always independent of the speedup. And then, yes, for the later stage, I mean, there is less known about the internal values.
Okay, thank you.
Are there any questions or comments? Okay, if not, let's thank the speaker again, and let's thank all speakers of this session. Enjoy the coffee break.
Test, test. Can I put it in my pocket?
Okay, it's time to start session of block cipher 2. We have 3 talks. First talk is a new algorithm for unbalanced meet-in-the-middle problem by Ivica Nikolic and Yu Sasaki. A talk is given by Ivica.
Thank you. Okay, so first let's try to understand the meaning of this unbalanced, excuse me, meet-in-the-middle attack with a simple example. Imagine you were lucky enough or smart enough and managed to invert the compression function of SHA-256. Say in 2 to the 64, you can find pre-image for the compression function. And now you want to convert this pseudo pre-image attack into a pre-image attack for the hash function. So how you do it? Well, of course, use the well-known meet-in-the-middle attack. So basically, you are using 2 compression function calls. This is your IV. This is the target hash that you want to find pre-image for. So first, you create a set of 2 to the 96 pre-images using the pseudo pre-image attack. You store this set in the hash table. And then from the IV, you shoot with 2 to the 160 images for the first compression function. Because the middle space is only 256 bits wide, you can hope to find, on average, 1 collision. Okay? So this is the typical meet-in-the-middle attack. So why is it unbalanced? Because as you have seen, the cost of this function is 2 to the 64, whereas the cost of this function is only 1. So that's why we call it unbalanced meet-in-the-middle problem. Okay? That's the only thing. So this function costs more than this function. Everything else is pretty much the standard. Now, Diffie and Hellman introduced the meet-in-the-middle problem some 40 years ago, and they called it meet-in-the-middle. They introduced the problem for finding the keys of double deaths. So they call it meet-in-the-middle because they are indeed the 2 encryptions with 2 independent keys for meeting in the middle. However, today, when we talk about meet-in-the-middle, we have in mind some more general meaning. For example, the latest attack on AES, the Demirci Seljuk meet-in-the-middle attacks, have nothing to do with meeting in the middle of the cipher. It's not that you have, I don't know, 8-round AES, and then after 4 rounds, these 2 encryptions are meeting. No. There you have an offline phase where you create some pre-computation table, and then in the online phase, you shoot into this table. Okay? So it's not meeting in the middle. So basically today, when we talk about meet in the middle, what we mean is nothing more than a collision search between 2 functions. Okay? Whenever you hear the word meet in the middle, forget about meeting in the middle of the cryptographic primitive, but think about collision search between 2 functions. And that's how we're going to regard this problem here in this talk, and that's how you should see the problem always. So we are trying to find a collision between 2 functions, f and g. So we're trying to find 2 values, x and y, such that f of x equals g of y. That's all. Now we can differentiate several types of collisions between f and g. The most common types when f and g have a range larger than domain. That's the first type, and the second time when the range is not larger than domain. And in this talk, I'm going to focus on the second case. And further, we can simplify it even further, and then we can assume that we are dealing only with n-bit functions f and g, and we are trying to find a collision between these 2 functions, but we are looking for unbalanced collisions. So we introduce this value of r, so we assume that one of the functions, let's say g, is r times more expensive than f. So in the previous example of SHA-2, g was 2 to the 64 times more expensive than f. Okay, so r equals 2 to the 64 divided by 1 equals 2 to the 64. Okay, so now let's take a look at the state of the art. What are the best known algorithms that solve the unbalanced collision search problem? Well, when I equals 1, actually this is the balanced collisions, of course we use the Floyd cycle finding algorithm, and we can find collision between two functions in time 2 to the n divided by 2, and this algorithm doesn't require any memory. When r equals 1, as we saw in the case of SHA-2, we use the meet in the middle. So basically we store square root of n divided by r images of G, we store in a hash table, and then we produce around square root of r times n images of f to shoot in the hash table, and because the meet in the middle space is n, when you multiply the sizes of these two sets, you're going to get n, so on average you can assume you got one collision. So you can see why we disbalance here the number of calls and number of calls, because G costs r times small. So even though we produce this many images of G, because it costs r, so the total time complexity for producing the first set is square root of Rn, same as in the second case. Okay? So this meet in the middle requires time of square root of Rn, and memory square root of n divided by r. In general case, I'm quite sure that all of you know that the meet in the middle follows the famous trade-off, time times memory equals n. But keep in mind, the time cannot be less than square root of Rn. You can easily show this, okay? So let's try to remember. The minimal optimal time is square root of r times n. Okay, so we have this, excuse me, nice algorithm that can solve, that has been used for many, many years. Why do we have to come up with a new algorithm? It works perfectly fine. Well, it's a bit strange. So in the case when, so here on this chart, I have the dependency, how much memory do you need, depending on the ratio of the cost of the two functions, if you want to find the collision in optimal time. So this is log of r, this is log of m. So when log of r equals 0, in other words, when r equals 1, in other words, the balanced case, so when the two functions are balanced, we don't need any memory to find the collision. And now look at this. We increase r slightly, a little bit we increase, and then the required amount of memory jumps to square root of n. So even though we increase slightly, the memory jumped to square root of n. And as you can see, it's kind of counterintuitive. The larger the ratio between the two functions, the less memory we need. So imagine one of the functions is 4 times more expensive, only 4 times more expensive. And then in order to produce the collisions in optimal time, we need square root of n memory. Okay, so because of this kind of discrepancy, we are trying to come up with a new algorithm. Okay, so let's take a look at the new algorithm. So the new algorithm combines two ideas. The first is unbalanced interleaving or unbalanced selection function. And the second one is one-shot Wiener parallel collision search. So let's first take a look at the first idea. So as I mentioned before, in the balance case, how we find collisions between two balances, of course, we use the Floyd cycle finding algorithm. In other words, we define a new function, h of x. We, depending on some selection function that's either 0 or 1, so h of x either equals f of x or g of x, depending on this function that outputs 0 and 1 with equal probability of 1/2. Okay? And then we run Floyd for this function h of x, we find a collision. And after finding a collision, we check if it's a collision between ff or fg or gf or gg. So in half of the cases, it's the good collision that we are looking for. So if it's a bad collision, we have to repeat the search. On average, we have to repeat the search only twice. So to put this into perspective, this is your function f, this is the raw, this is the cycle finding algorithm. So as you can see, evaluates either g or f randomly. And then once we find a collision, which is here, let's say, so it's between G and G, so this is not good. Obviously, we have to repeat again. And after repeat, we found a collision between F and G. Good, we can use this as a collision. So this is the balance case. Now, unbalanced interleaving happens. Exactly everything is the same, just the selection function outputs 0 r times more than it outputs 1, meaning this function h of x equals f of x r times more often. And now when you produce a collision for h of x, it's a collision between f and f with much higher probability. If you want to be a collision between, the probability it's collision between f and g is only 1 divided by r. And that's why you have to repeat the search r times. Okay? So again, we put this into perspective. You can see now, excuse me, you have much more invocation of function f than g. So we run Floyd cycle finding algorithm, we find a collision, but of course it's between F and F. We run again, it's again F and F, and after repeating this around R times, we're going to find a collision between F and G. Okay? So we have this unbalanced collision. Why don't we use this as a new algorithm for the search of unbalanced collisions? But the reason is, so you can see the complexity of this algorithm is one cycle finding costs square root of n, and we have to repeat this R times. So the complexity is R times square root of n. But optimal time complexity was square root of Rn. So we kind of add factor of square root of R to the time complex. So this is not optimal. We need some more advanced ideas. And the second idea, and this is the more advanced idea, is instead of finding collisions with the Floyd cycle finding algorithm, we're going to use Van Oschot-Wiener algorithm to find a collision. So this is very famous and very frequently used algorithm whenever you want to find multiple collisions. If you're looking for a single, you always run Floyd. If you want multiply, you always switch to Van Oschot-Wiener parallel collision search, or as I like to call it, multiple collision search. So, however, unlike Floyd algorithm, this algorithm requires memory. So let's take a look how it works. It works in two phases. In the first phase, you build a hash table. So basically, you start with 2 to the m random points, and you iteratively, so assume we are trying to find a collision for some function f. So you start with 2 to the m random points, and you iteratively evaluate the function f on those points. You build for each of the points, you build a chain that's, build a chain of length 2 to the n minus m divided by 2. And then you store in a hash table only the n, and only the ending and the beginning points of each chain. Okay? So we create a hash table. And then when we are trying to find a collision, we take a random value and start evaluating, again, building this iterative chain. And every time we extend by one value, we check if the newly constructed value coincides with one of the stored points of the chains. So if it does coincide, obviously it collided this chain somewhere with this chain. And because this value we also have in the table, we can backtrack and find where collision occurred, and thus we can find a collision for f. So as you can see, during the construction of the table, it has 2 to the m points. The length of each chain was 2 to the n minus m divided by 2. If you multiply this thing, you can see that when we were constructing the table, we passed this many values. And if the length of this chain, and because in total there are 2 to the n values, if the length of this chain is 2 to the n divided by how many points here, we get if the length of the chain is this much, then on average we're going to find a one collision, so the algorithm works nicely. So the total time complexity to build a hash table and find collisions, so to build the hash table is 2 to the n plus m divided by 2, and it requires 2 to the n memory. And to find s collisions, s time, we have to find a collision search algorithm. For one, we pay 2 to the n minus m divided by 2. And now we can present our new algorithm for unbalanced collision search, excuse me, or unbalanced meet in the middle. So we define the function h is unbalanced interleaving between f and g, and this sigma outputs r times more 0 than 1. So basically, h of x equals f of x r times more frequently than g of x. And then for this function h of x, we construct a hash table according to the Van Oschot-Wiener algorithm with this many entries, this much memory. And then we find a collision for h of x. If it's collision for f and g, excellent. If it's not, we have to repeat the collision search algorithm. So basically, because h of x equals f of x r times more often, we have to find on average r collisions in order to find the to solve the unbalanced collision search problem. So again, to put this into perspective, this is the hash table. So again, as you can see, there are many more evaluations of f than g. Now the whole trick why this thing works, see here, even though I have many more f's than g, but keep in mind the cost of g is r times more than the cost of f. So basically how much I paid here, I paid the same time complexity for f and for g. That's the whole trick why the whole kind of algorithm works, because of the construction of the hash table. And then of course I find a collision. I check, no, it's a collision between f and f. I find another collision now between F and F, and after repeating this times, I'm going to get a collision between F and G and solve the unbalanced collision search problem. So the total memory complexity to the M, this much we pay for the construction of the table, this much to find our collisions. When this number is larger than this number, in other words, when M does not exceed R, then we end up with a very nice trade-off that says T square M equals R square M. Okay? So in order to solve the unbalanced collision search problem, you can use this algorithm which follows this trade-off curve. It's a bit familiar. So this algorithm, in comparison to the standard meet-in-the-middle algorithm, has a better time for certain values of M, better memory for certain values of M, and what's most important, or one of the most important things, is the unbalanced collision search, where one of the functions is R times more expensive than the other function, can be solved in the optimal time, T equals square root of Rn, with not more than R memory, okay? So this is the Floyd. For the balance case, this is the old meet in the middle, the standard meet in the middle, and this is our new algorithm. When we are trying to find the optimal, when we are trying to find the collision in optimal time. Okay, so now actually the amount of memory is not 2 to the n divided by 2 around when the ratio of cost is close to 1, but actually the smaller the ratio, the less memory we need. So obviously here, from 0 to 1/3, our new algorithm outperforms the standard meet-in-the-middle algorithm in terms of memory. However, you should also know that sometimes in some of the problems, the ratio R of the cost of the two functions depends on the memory, so you cannot just simply use the trade-off that I presented, so you have to come up with a new trade-off. And also, the new algorithm will not work if one of the functions is given as sets, okay? Because in order to work, we have to evaluate both f and g on certain random points. And because we need to evaluate on random points, we cannot use our algorithm in a known plaintext attack. It's always chosen plaintext. Also, in some papers I've seen, some of the people say, we actually do not care about memory complexity, we're just interested in time complexity. If that's the case, keep in mind, both the standard and the new algorithm, they achieve the minimal time complexity. It cannot go any lower. So if you don't care about the memory, you can just ignore the new algorithm. If you do care, you should probably take a look. But keep in mind the algorithms that use infeasible amount of memory, they are completely entirely useless in practice. So you should care about memory. So the new algorithm may replace the standard, depending on the ratio R, as we saw from the chart. And in our paper, we have certain number of applications. You can take a look there. We, of course, didn't go through all the papers that use standard meet-in-the-middle algorithm and try to replace with R, because it's kind of trivial to do so. What's more interesting, actually, certain balanced collision search problems can be reduced to unbalanced and then solved using our algorithm. For example, when you're trying to find collisions between two functions, but for one of the functions you have to pay data complexity. So each evaluation of the function means one query to the cipher. So if you want to reduce the number of queries, you want kind of to switch to the unbalanced case, and then you can use our algorithm. Or if one of the functions has a reduced domain size, again, this is reducible to unbalanced collision search. And to conclude, you should consider a new algorithm whenever you're dealing with unbalanced meet-in-the-middle problems. The rule of the thumb is the ratio of cost of the two functions is less than 2 to the n divided by 3, then probably you should use our algorithm than the standard meet-in-the-middle algorithm. In some of the open problems, you can try to find more tricky cases, use cases of the new algorithm, and maybe try a new algorithm for the known plaintext case, so basically when one of the functions is given as a set. That will be really nice. And that's all. Thank you.
Any question and comment?
Small comment about the case in which the function g is a function, not a permutation, not uniquely invertible. if you are trying to build the tree backwards, actually it has only a linear number of possible values. So if I go back for t steps, the expected size of the number of predecessors, which are t away from the final point, is only order t. Because even if I try to go back,
yes,
and
but
I got
some of them.
2 or 3 possible values, some of them might not have any predecessors,
Yes.
and therefore some branches die out. And this is a well-known combinatorial property that actually the number of predecessors, even if you go a very long way backwards, is very limited.
Yes.
So you might want to use it in your attack, even when you have a set.
Okay.
Comment and question. I have one question.
Yes.
In your algorithm, you consider 2 functions, f and g. How about the more function 3 and 4 function for general burst problem? Can be applied?
But 3 is terrible, actually. We cannot do anything for 3. 4, we can do something, because 4 is kind of 2 plus 2. 3 is one of the most interesting problems I think we have and everybody in computer science has. But no, I don't even know for case 4. Probably something can be done. I cannot say it right now.
Okay, let's thank speaker again. The second talk is applying MILP method to searching integral distinguishers based on division property for 6 lightweight block ciphers by Jung Cheon, Wen Dao Zhang, Zhen Bao, Dan Dai Lin. Talk is given by Jung Cheon.
Good afternoon, everyone. My name is Zejun Xiang. The title of this talk is Applying a MILP method to certain integral distinguishers based on division property for 6 lightweight block ciphers. This is the overview of the talk. Firstly, we will review division property, and then we show how to combine a MILP method with division property. At last, we present a search algorithm and show some applications. First of all, we should take a look at some new notions. For any fixed u, pi ux is a Boolean function. It's divided as the product of some chosen bits of x, and we use vector u to choose the corresponding bits. So if n equals to 4, m equals to 2, pi ux can be computed as 0 to the power of 0 times 1 to the power of 1, and so on. So the value of pi ux equals to 0 in this particular situation. Next, if k and k star are 2 vectors, if ki is greater than or equal to ki star, so in this case, we will say k is greater than or equal to k star. Otherwise, we say k is not greater than or equal to k star. Now we review the definition of division property. Division property is introduced by Todo at Eurocrypto 2015. It's a generalized integral property. Let X be a subset of F2n to the power of m, and Ki be m-dimensional vectors. X has the division property dk0 k1 to kq minus 1 if the sum of pi ux equals to 0 for all u belongs to this set. In this expression, wu represents the vectorial Hamming-weight of u, and the wtu0 represents the Hamming-weight of u0. So now, with the help of division property, we can search integral distinguishers for block ciphers. Firstly, we need to construct an input set with division property dk0, and then we propagate the initial division property around to get dkr. At last, we try to extract some useful integral property from DKR. So in order to use division property, we need to know the propagation rules. Next, we show some propagation rules for division property. For copy operation, the division property propagation is just to decompose the k value into all possible combinations. For XOR operation, the division property propagation is just to add the two coordinates of the input division property. For AND operation, the division property is to try to find the maximum value of the input division property. Now the division property is defined and computed on F2n to the power of m. If n equals to 1, this is the bit-based division property. So bit-based division property treats each bit independently, so it can describe much more detailed division property, and it can find longer distinguishes and better result. But however, bit-based division property need much more computations. At FSE 2016, bit-based division property can only apply to Simon 32 and CMAC 32. So in the following of this talk, we focus on how to compute bit-based division property efficiently. The overall strategy here is to use mixed integer linear programming method to characterize the division property propagations. MILP problem tries to find the minimal or maximum value of an object function on some linear constraints. In this model, M is a constant matrix, A is a constant vector. A part of all the variables in X are restricted in integers. So in order to complete this conversion, we need to address two issues. The first one is to describe the division property propagations by linear inequalities. The second one is to convert such program to estimate the minimum value of the object function. To facilitate this conversion, we present a new launching here. Assume the input set to the block cipher has initial division property dk, and denote the division property after I round encryption by dki. So we have this chain of division property propagations. For any k0, k1 to kr belongs to the product space of big K0 to big KR. If Ki minus 1 can propagate to Ki for all I, then we call K0 to KR an unround division trio. So based on the definition of division trio, we can say that the set of the last vectors of all R-round division trios which start with K is equal to KR. So now give an input division property, we do not need to compute K0, K1, K2 step by step. We only need to find all the division trios and check the last vectors of the division trio. But still, we don't know what kind of property we should check for the last vectors. So this proposition gives a sufficient and necessary condition of a set to have no integral property. Assume X is a set with division property dk, then X does not have integral property if and only if K contains all the n-unit vectors. So in this case, give initial division property dk and round number R. There doesn't exist R-round distinguisher if and only if there exist n division trios which start with the initial division property K and ends up with the n-unit vectors. So now the problem is quite clear. We just need to find n division trios. Next, we can proceed to the first issue. Describe the division propagations by linear inequalities. We will address these issues by modeling some basic operations used in the block cipher by linear inequalities. The first one is the copy operation. This is the general propagation rules for division property. And for bit-based situation, n equals to 1. Based on this propagation rule, we can find 3 division trios for copy operation. And then, if A to B0, B1 is a division trio of copy operation, this equality is sufficient to describe these propagations, because all the feasible solutions of this equality are all the 3 division trios of copy operation. So similarly, for XOR operation, this is the general propagation rule. And for bit-based situation, n equals to 1. For this case, we can compute 3 division trios for XOR operation. For this particular situation, K0 and K1 equals to 1, this propagation will abort, because in this case, K0 plus K1 equals to 2, which is greater than 1. Since we consider bit-based division property here, so this division trio is invalid. Next, if we denote A0, A1 to be a division trio of XOR operation, this equality is sufficient to describe these propagations. Now for AND operation, this is the general rule, and this is the bit-based situation. So we can compute 4 division trios for AND operation, and we can compute 3 inequalities to describe the propagation. We can check that all the feasible solutions of these 3 inequalities are the 4 division trios of AND operation. Next, we show how to model S-box. We take present S-box scale as an example. Assume this is the input division property of S-box, and we calculate the algebraic normal form of present S-box. So from this input division property, we know that only the sum of these 2 monomials are unknown. But we can observe y0, y2, these 2 Boolean functions does not contain these 2 monomials. So the sum of y0 and y2 are 0. Moreover, we can compute y0 times y2, and we found y0 times y2 does not contain these 2 monomials. So the sum of y0 times y2 is also 0. Based on these observations, the output division property should be D0010 and 1000. So follow this similar idea, we present a generalized an algorithm to compute the division trios of any S-box. The input to the algorithm is the input division property of n-bit S-box, and k equals to kn-1 to k0. And the output is a subset of all n-dimensional binary vectors, such that the output division property is dk. So firstly, we initialize S bar as all the vectors greater than or equal to k. And according to the definition of division property, fx denotes all the unknown monomials. So for all u belongs to f2 to the power of n, we compute pi uy and check if this Boolean function contains any monomial of fx. If so, the sum of pi uy is unknown. And in this situation, we add u to k bar. At last, we run a size-reduced procedure on k bar to return k as the output. So based on this algorithm, we can compute the division trios for present S-box. These are the 47 division trios we found for present S-box. This entry marked with red are the 2 division trios we computed in the example. So now for any n-bit S-box, we can compute 4 division trios by the algorithm, and then we treat the division trio as 2 n-dimensional vectors. At last, according to Sun's idea, we can compute a set of linear inequalities with the help of Sage software, and all the feasible solutions are all the division trio. So these are the 11 inequalities we found for present S-box. In this inequality, A3, A2, A1, A0 denote the input division property, and B3, B2, B1, B0 is the output division property. So now for any block cipher based on copy, XOR, and S-box operations, we can construct a linear inequality system to describe the division property propagations, but still we don't know the division property of each round. We don't know K0, K1, because this linear inequality doesn't contain any information of the input division property. So if this is an R-round division trio, and let k equals to kn-1 to k0, we should add a0i equals to ki for all I into the model. Now the input division property has been added into the model. So we know K0, and then according to the propagation rules, we know Ki, K1, K2, Kr. Thus we have solved the first issues. Now we can proceed to the second issue, convert the search program to estimate the minimum value of the objective function. And we know that if Kr contains all the n-unit vectors, R-round integral distinguisher doesn't exist. So if this is an R-round division trail, we can set the sum of the coordinates of the last vectors as the objective function. And we try to find the minimum value of this objective function. If the minimum value of this objective function equals to 1, then we have found a unit vector. So now for any block cipher, given an input division property, we can construct a set of linear inequalities to describe the division property propagations for the input division property. And then we set the sum of the coordinates of the last vectors as the objective function. Combine this set of linear inequality and the objective function, we can get a MILP model. And this model will be the input of the search algorithm. And the output of the search algorithm is a set S, and this set will indicate the balanced bit positions. Firstly, we initialize S as all the possible bit positions, and then we try to repeat this procedure n times. N is the block size of the block cipher. And for each time, we check if M has feasible solutions. If so, we optimize this model and try to get the objective value. If the objective value equals to 1, we have found a unit vector, and we let P denote the bit position, take a value 1 in the objective function. In this case, P is an unbalanced bit position, so we need to exclude P from S and remove the unit vector from M, and we try to optimize this model again. So if this procedure stops, we will get a set S as the output. If this set is empty, then R-round integral distinguisher doesn't exist. If this set is non-empty, then we have found some balanced bit positions for R-round encryption. This table shows some applications of this search algorithm. We can find that we can find better result for Simon and CMAC block ciphers except for Simon 32 and CMAC 32. We can also find a better result for present and rectangle block ciphers. For the last two block ciphers, we find the same result. We can find the same result as the previous best result. The more important data is this column. This column shows the execution time of this search algorithm. And among these ciphers, Simon 128 took the most time, but it's still less than an hour on a personal desktop. So this algorithm is quite efficient and practical. Okay, those are some references. Thank you.
Any question and comment? We have a lot of time to discuss.
Can you please go to the slide where you show the objective function?
Here?
So you're trying to minimize, again, what are you trying to minimize?
We try to find the minimum value of this expression, the sum of the coordinates of the last vector of the division trail.
Question or comment? Okay, let's thank speaker again.
this right eventually.
The final talk is reverse cycle working and its applications by Sarah Miracle, Scott Yerek.
Right, it's that side. Right, that way. All right, can you hear me? Yes, all right. I'm not sure I still have this right, but all right. That is not my slides. Thank you. All right. All right. I'm going to go ahead and get started here. We'll see if I can figure out the technology. Okay, so I'm going to talk about the following problem. All right, suppose you're given a block cipher on a set T, and you have a smaller set S, which is a subset of T, and our goal is to use our block cipher on our set T to find a block cipher on our smaller set S. All right, I'm going to give you a new algorithm to do this, and I'm going to start off by telling you a story to motivate this problem. Then I'll give you the new algorithm, or I'll give you a little bit of background on the problem and existing solutions. I'll tell you about our new algorithm, and then I'm going to end by giving you a few proof details, but there won't be too many of them, so I'll go through that pretty quickly. All right, and this is joint work with Scott Yellick. Good. All right, old-fashioned way. Okay, so this is motivated by the application by format preserving encryption. So here's the setup. Suppose you have an existing database that stores some sort of information. So for example, maybe you have an existing database with millions of US Social Security numbers already set up there, right? So your customers have applications, there's hardware, software involved, it's already set up. And you come back later and decide, hey, we want to add encryption to this database. So how are you going to do this? And this data that you have has some special conditions. So for example, for Social Security numbers, these are 9-digit numbers, and there's some restrictions. For example, the first 3 digits can't be 666, and there are all kinds of other restrictions associated with this data. Okay, so how are you going to do this? Well, one basic first pass idea is we could represent these Social Security numbers as 30-bit numbers, pad with some extra zeros, and then encrypt using just standard block cipher. But in some cases, this doesn't work because the encrypted numbers have a significantly different format, could have a significantly different format from the original format. And this can cause all sorts of problems with your application, hardware, software, et cetera, that you don't want to have to fix. So the idea is that we want to generate ciphertexts that have the same format as the original data. So these are actually valid Social Security numbers. They don't start with 666, et cetera. All right, so that's our goal. All right, so let me go ahead and tell you a little bit about the background and what we know so far, and then I'll tell you about our new algorithm. Okay, so in many settings, we already have solutions that can do this. So for example, if your set S are bit strings or integers up to 9, there's lots of work showing how to solve the problem in these cases. Also, if your target set S has an efficient way to rank or unrank the elements in your set, then you can simply use this algorithm and then a cipher on the set of integers from 0 up to the size of your set minus 1. So we're looking at the situation where basically all we know how to do is test membership in the set S. So we know how to find whether something is in the set S or not, but that's just about it. Okay, so here's the general approach to this problem is, again, we find a cipher on some larger set T, which contains our set as a subset. Then we transform it into a cipher on our smaller set S, and this is the problem I started with at the very beginning. So for example, in the Social Security setting, we can use the larger set S, let that be the set of 30-bit strings. We have many ways to encipher this. And then we need to tackle the second step, right? So how do we take this cipher on the set T and get a cipher on the smaller set. And one of the kind of canonical ways to do this is called cycle walking. And the idea is that if you have a point in your smaller set S, you evaluate the permutation on your larger set, and you check, okay, did I get a point that happens to be an S, right? Because we can test membership in S. And if you get a point in S, great, you're done. If you get a point in T, well, you do it again, okay? And if now you get a point in S, again, you're done. If it's a point in T, you keep going. And basically, you do this until you hit a point in S. And you're always going to eventually hit a point in S, because maybe you'll come all the way back around to the point itself, but you'll get there eventually. Okay. So we're going to take a look at this algorithm from the cycle structure perspective, because it will be useful when I introduce our new algorithm. But essentially, if you look at your permutation on T in the cycle structure, the effect of cycle walking is simply to cross out all the elements in S, or sorry, all the elements that aren't in S, and we're left with a permutation on S. Okay, pretty straightforward so far, hopefully. All right, so cycle walking was formally analyzed by Black and Rogaway in 2002. And they showed, or well, as you can see, right, there's running time of this algorithm has expected running time, constant time, assuming that the size of S is a constant fraction of T. But in the worst case, it's not so great, right? Because in order to evaluate a single point in S, we might have to go through basically every single point, in the worst case, every single point that's in T but not in S before we find a point in S. Okay? In addition, right, this algorithm can take different times depending on the permutation and depending on the point. So it's possible that maybe the fact that we have different running times can leak some sort of information. Now, Belair, Ristenpart, Rogaway, and Stigers did show that in a certain setting, this doesn't actually leak any information and it's not damaging, but you can envision that maybe there's a setting where this could cause problems. Okay, so the question, our algorithm, or what we looked at was, can we do better? So can we improve this worst case running time, and can we come up with an algorithm that doesn't leak any timing information? All right, so finally, our algorithm. Okay, so let's consider the cycle structure. One idea you might have is, can we somehow cut this algorithm off early, right? Can we somehow, if we're in that worst case situation, can we cut it off early and maybe just accept some sort of error? But it's not clear how to do this with cycle walking, because we still need to end up with an actual permutation, right? Somehow we have to get a point in S. So here's the idea. So we're going to go ahead and take our point that we want to evaluate, and we're going to evaluate our permutation on T. And if we get a point in S, then again, we're going to stop, just like we did in cycle walking. But if instead we get a point that's not in S, a point in T, so for example, if we're trying to find out what 2 gets mapped to, then instead of continuing on, we're actually going to go backwards instead. Okay, so we're going to go backwards until we hit a point that's not in S. And essentially what this is going to do, the effect it's going to have on the cycle structure is, again, we're getting rid of all the points that aren't in S, but now we're only looking at contiguous points in S. Okay, so we're only looking at contiguous points in S. So this single cycle here in our original permutation is going to get broken up into 2 different cycles, which are the contiguous points in S. Okay, so if you're following me so far, you're probably thinking to yourself, wait a second, this hasn't actually improved the worst case running time too much, right? Because in the worst case, we still might have to go through every point in S, and if S is a constant fraction of T, then, all right, this is not very satisfying. Okay, I mean, it's a smaller constant fraction, but, okay, so here's the further idea, and that is that we're just going to look at 2 cycles. Okay, so we're going to look at these contiguous points in S, and if they're more than 2 points, we're just going to get rid of them. All right? So we're only going to look at 2 cycles, and so we're going to be left with essentially a matching at that point. Okay, so just to give you another example, again, we're eliminating all the points that aren't in S, and then we're only looking at the contiguous points, and any cycle that's longer than 2, we're just going to get rid of, and we're going to map all those points to themselves. Okay, so here are the formal details of the algorithm. It's It's not as complex as it looks, but we've added an extra bit flip. So in addition, those points that get mapped to something besides themselves, we're going to flip a bit, and if the bit, flips one way, we're going to use that pair. If not, we're just going to map those points to themselves. And this actually happens to be useful when we get to the proof, which we probably won't go into too much detail today. But the big thing to note is that you only have to evaluate the permutation on 3 different points in the worst case. So in the worst case, it takes constant time. OK, so one, in every case, it takes constant time. So one step takes constant time. That's great. But even if the permutation on T is random, this new permutation that we've generated is certainly not random, right? And you can pretty easily see that in that a lot of points are going to get mapped to themselves, right? So this isn't random. It's not even a random matching, and it's not a uniformly random matching. So the question becomes, OK, so it's not random, but if we do it enough times, it is random. So now we ask the question, how many times do we have to repeat this process before we get a permutation that's close to random? And at this point, this is essentially a Markov chain. And we can use techniques from the Markov chain community to answer this question of how many times do we have to apply the algorithm, and we're really hoping it's less than the size of S to get an improvement on this algorithm. And it turns out the answer is logarithmic in the size of T. So this is going to get us an improvement in the running time. OK, so what are the advantages of this algorithm? So we have an improvement in the worst case running time from O of, all right, so now I'm switching to Markov chain community, right? So N is the size of T here. So we go from linear to logarithmic in this worst case. We have no leaked timing information here, so everything is going to take the same amount of time to evaluate. In addition, we can now trade off security and running time. So you can choose, OK, maybe I don't want to do the full log n steps. I can make a trade-off depending on how secure or how random I need my permutation to be. In addition, we're going to have some other benefits, like increasing the level of security. And the reason we get some of these, and I won't go into too much detail on it, is that essentially we only need to evaluate the points in S. We don't need to evaluate the entire permutation in the worst case. OK. All right, so I'm going to talk to you a little bit about some of these proof details, but not too much detail. OK, so this question of how many times do we need to apply the algorithm before it's close to random is essentially the question of what's the mixing time of this Markov chain. So I have it defined formally here, but essentially we're looking at how long do we have to go before the variation distance is less than some epsilon. OK, so in order to bound the mixing time, we're going to show that our algorithm yields what's called a matching exchange process. And a matching, I'll tell you what that is in a second. But essentially, it was defined and analyzed by Sumaj and Kulowski in 2000. And we're able to use a lot of the same techniques that they did to come up with a bound on the running time of our algorithm. And we do some modifications, and we dig into their proof, and we give some explicit bounds. So they give a big O bound, but no constants. And we reprove several of the key lemmas in the context of our setting. So they prove a more general bound in a more general setting. OK, so we do some customizations for our algorithm. So I'm going to start off telling you what the matching exchange process is, and then I'll dig in a little bit into the details. OK, so a matching exchange process works as follows. You begin by choosing a number kappa according to some distribution. Then you pick a matching of size kappa uniformly at random. And then for each pair in the matching, you're going to transpose the 2 points with probability 1/2 and otherwise do nothing. And this is where that bit flip in our algorithm comes in to play. So it's pretty straightforward to see that our algorithm is a matching exchange process. Although we're not generating the matchings uniformly at random, a matching of a certain, if we look at all the matchings of a certain size, those all have the same probability. All right. OK, and their theorem says that as long as the expected value of kappa is O of n, then a matching exchange process mixes in time O of log n. Okay, so in order to analyze the mixing time of this process, your first pass approach might be to use the technique of path coupling, which is a fairly standard approach in the Markov chain community. And essentially what you do is you take a look, in our setting, you're going to take a look at two permutations, and we're thinking about these now as permutations on S, that differ by a single transposition, so a transposition of a single pair of points. And then we're going to simulate our process on those two different permutations. And the time that it takes until our process meets gives us a bound on the mixing time. OK, so when we apply this in our setting, we consider two configurations that differ by a single transposition. And if the first matching that we get at the first step, if it contains the specific pair, then we can essentially use this matching for one of our use this pair for one of our processes and not use it for the other one. And the two matchings, permutations will meet after a single step. If it doesn't contain this pair, there's not a lot we can do. And the problem is that this pair only comes up with probability 1 over n. Okay, so this isn't going to work because this will give us a bound of n log n, which really hasn't helped us at all. It just got worse. Okay, so what they do in the case of the matching exchange process to get a better bound, here's the high-level approach. Instead of looking at what happens to this process over a single step, they look at what happens over log n steps. Okay, so they look at it over a longer period of time using a technique that's called delayed path coupling. In addition, they're going to use what's called a non-Markovian coupling. So they're going to use some information about what happens in the later steps to choose some of these matchings for the two processes. OK, so I'm just going to I'm going to do this fairly quickly, give you a high-level idea of how this works. OK, so again, we have these two processes that we're trying to simulate. They start by differing by a single transposition, and we want to see how long it takes before they couple. And we're looking over log n steps. And one of the requirements is that if we look at a single one of these processes, it needs to look like our algorithm, right? So if we just look at that one in isolation, it has to look like our algorithm. But we can do things to help them along as long as they, again, if you just look at one, it looks like the process. OK, so for one of our processes, we're just going to choose the matchings like we would with the algorithm straight off, all right? But we're going to be selective in how we choose the matchings for the second process. All right, so here's the idea. Again, since these two processes start by differing by a single transposition, if we get that particular transposition, we're good, right? We're golden, if we happen to get that particular transposition. But that doesn't occur, that's not very likely to occur, right? That's our problem. But what is likely to occur is that our 2 points, u and v, get matched with other points, right? So maybe u gets matched with z and v gets matched with w, and this is likely to occur. And so what we can do is then, and we could choose these two matchings so that after one step, they differ by the u-v transposition, but we can also choose the matching so that after one step, they differ by this zw transposition, okay? And if in the next step after that, we happen to get either of these two transpositions, the uv or the zw, then we can fix everything. And essentially, the key important fact is that now the number of transpositions that fix our problem, now there's twice as many after one step. And essentially, we can show that after 2 steps, there are 4 times as many, and they double. And so we can take a look. And because these transpositions are doubling, we end up showing that after log n steps, we're going to have enough so that we're highly likely to hit one of these good pairs after that many steps. So that was pretty much all the detail I want to give you about that. But OK. All right, so we're going to call these good pairs. And essentially, the parts that we prove is we're going to show that after log n steps, with high probability, we're going to have a linear number of these good pairs. And thus, then we can show that with high probability, one of the next log n matchings is going to contain one of these good pairs. And that's the part that we end up reproving. OK, so in terms of future directions, it's, there's obviously things we can do to improve the algorithm. We don't think that this bit flip is necessary. It's really just makes the proof go through, but I don't think it actually improves the algorithm. But I think the more important one is that this expected constant running time that you get with cycle walking is very attractive, right? And we certainly don't achieve that, right? It's going to take us logarithmic time every time. So it's consistent and it has a better worst case running time, but it'd be nice to go back to that constant time. That looks very nice, right? Okay, that's it. Any questions?
A question, the comment?
So I was trying to go through a mental calculation on concrete numbers, and something seems to be wrong. Maybe I misunderstood your algorithm, but you gave the example of t being 2 to the 30, and let's look at s, which is 2 to the 20. So 1 in 1,000 numbers are good values. So if you are looking at a random permutation, the chance that a given good point is followed by another good point is only 1 in 2 to the 10, 1 in 1,000. So almost all the numbers are going to be singletons in your construction. Well, let me continue. So the probability that you are going to have a pair or larger cycle is going to be smaller than 1 in 1,000 due to the additional bit flip that you mentioned. Now you are repeating the whole thing only 30 times. And in 30 times, with probability of 1 in 1,000, almost always the singleton will be mapped to itself in the first application, second application, up to the 30th application. So with very high probability, still every point will be mapped to itself in your example. You somehow don't consider at all the ratio between S and T. You just do the number of iterations to be log T, regardless of how small S is within the range.
Yes, so I've hidden a little of those details from you. You're perfectly correct. So the numbers that I give you assume that S is a constant fraction of T.
Then it will work.
When you look at the theorems in the paper, everything is right. That ratio of the size of S to the size of T is critical, and that shows up in every theorem because it affects.
Fine. But you didn't say this is a crucial element, this parameter of
so
size of T to the size of S.
Yeah, so we assume it's a constant fraction.
A question?
Thanks for the talk. I had a question about whether you could generalize this argument. So it looks like right now you're sort of pairing up elements and then swapping or not. Could you take triples of elements or quadruples and permute them? Does that still work? Does the proof not work? What happens?
Yeah, so that's a great question. I mean, that was our original idea because, I mean, ideally, right, if you allow longer cycles, it should take fewer steps before it gets to be random, right, because it's closer to what the original permutation looks like. But we haven't gotten the proof to work out. So presumably there's some trade-off, right? If you allow longer cycles, you wouldn't have to go as many steps, but we don't have a theorem that's general in that case, but you should be able to get that.
Going a little bit further. If you go a little bit further in your attempt to find another good point.
Yeah, the proof falls through. I mean, you can do it, and I mean, clearly it should be faster, but how much faster is, we're not sure.
Other question? Comment? Okay, let's thank Sarah and all speakers again.
Okay. Are you in charge of? Yeah. So I'm the first one tomorrow. Is it okay if I put it myself tomorrow morning, or should I send it to you this evening?
So you can put it even immediately now. Is it okay?
I don't have it with me. I don't have any USB stick, but.
So it's up to you. It doesn't. It's no problem.
Okay, and can I test this thingy because there's so many people doing it in different ways?
Yeah. So it's a little bit difficult to use this one, and you can like this. So you put onto your ear like this, right?
Okay.
Yeah.
Okay.
Yeah.
So this one should be on the, it should
Hello?
be on the left part.
Wait.
Okay. And then there is a pointer.
Yes, there is a pointer. So you can see, so for this one you put then there is the pointer here, and from the next and the previous.
Okay.
So we should open one, for instance, enter. One. Yeah.
And if I send it this evening by email, will you put it the presentation, or it's better to put it myself tomorrow?
Sure. So it's up to you, even when you will be able to send via email, or you will.
I can send it via email for sure.
Yeah. Micro bên kia.
Yeah, for sure I can send it by email.
Yeah, okay.
Thank you very much.
Sure, được.
Hello. We will have a IACR meeting at 5:30 on the other room. Okay, on the main room. No, we right after the last session, so that we can save some time.